going to take the time to try and do three things at once. I'm benchmarking using Camtasia Studio on my office desktop. I'm using a new webcam, Logitech 920, that also works across my Mac and my PC. And I'm going to introduce you to some effect size calculators that I have found to be particularly useful. At this point in my Psychology 205 course, we have just covered single sample hypothesis testing, single sample T, single sample Z, independent T, and related T. I thought this might be a good place to introduce the calculation of effect size statistics. Let's go for a minute then, if I don't lose my voice. Show you a blog in progress, and I will be incorporating this screencast into the blog. This is something I'm writing right now called Something Old, Something New. That is, how do I blend the foundation of my Psychology 205 course, which has proven to be pretty successful, with some of the so-called new statistics, effect sizes, power, confidence intervals, things of that sort. I'm going to just read here right now. I'll probably have to defer until this summer, mastering the intricacies of the new statistics championed by Jeff Cumming. And were you to click here, you'd have a link to the videos that he has graciously provided that essentially are covering the kinds of things he covers in his book by the same name. However, here is a first attempt to introduce the concept, calculation, and interpretation of effect sizes into my teaching. And right here as well, I will introduce this screencast once I'm done. Here are 5 effect size calculators I found useful enough to share with my students in Psychology 205. The one I'm primarily going to focus on is this one that says Hong Kong, that was developed by a guy by the name of Paul Ellis, who's written a wonderful book, actually a series of books, one that deals with effect size frequently asked questions, and another deals with power and how to calculate power. And I strongly urge any reader, any follower of this blog, to get a copy of each. He's playful, he really knows what he's talking about. Let's take a look. This is his effect size calculator, and I'm going to use this and concentrate on a couple of independent T examples, maybe one is enough, that I gave my students to work by hand. I have also calculated the effect size cones D and R squared by hand also, and it does give these same answers. But this is a whole lot more fun and a whole lot easier. It asks for the mean, the standard deviation, and the N of each group. In this case, I'm using an example from Gravitter and Wallnow. It's problem number 23, page 349, in which we have one condition, it's a well-lit room, and another condition is a dimly lit room. And this is for an independent group's design. And that's very important because you calculate your effect size statistics differently for a between subjects than a related group's design. This particular example, the mean in the well-lit group is 7.56. And I tabbed, and the standard deviation is 2.30. That's the unbiased standard deviation. And I have 9 individuals, and I'm tabbing to the next line. And my other condition, I had 11.33, and it was 2.18. And I had 9 in that condition also. And then you got to be careful here. At this point in time, you would hit compute. There is cones D, and the value of cones D and sign is irrelevant, is 1.68. And then there isn't a whole lot of agreement right now among statisticians about which effect size calculation to make or how to calculate it. And here are some alternatives. Here's glasses here's glasses delta, and hedges G, and you can see they're slightly different. But the preferred, the most frequently reported measure, the measure that APA journals seem to like, is the cones D. And then, alternatively, another effect size statistic coming from a slightly different family is those based on Pearson's R. And the statistic that usually is reported is this R squared, because you can think of this as a percentage of variability accounted for. And so you can account for about 41% of the variability here. It's a straightforward procedure to go between one or the other. When you're talking about Cones D, and that effect size descriptive statistic, you're essentially talking about standard deviation units of difference. Formula-wise, this is the difference between the two means divided by the pooled standard deviation, is how one would get that. All right, so that's one example of this. Why don't I go back just for a minute to the post, just to show you some of these other calculators. I found this one by Becker of some interest. And you can see right now this is set up. It's actually in Professor Becker's course, online course. Pretty much the same. They're the means and standard deviations, and there it would give you those. And it gives you many different flavors of this. Let's ignore that right now. Here is one from Psychometrica. So that I don't make this too long. And this is kind of nice. Slight variations. There's comparison of groups with equal sizes. There's your Cones D and your glass when you have different samples. Pre-test, post-test control with the corrections. So this is getting at some of the controversy about what is the right way to do this when you have a related groups design. I'll speak to that another time because I don't want to make this screencast too long. And here is a fourth that I found kind of useful. Particularly when you're trying to find effect size for some of the other statistics that I teach or I will be teaching. Last thing I want to show you here, we need not look at all of them there. I want to go back just for a minute to Paul's work that I so admire. And let's do one more example, and this time I want to go through his funky little subscripts there. We are comparing the effect of potential concussions on individuals in two groups. We have one group that is swimmers and one group that is soccer players. Here is the mean for the swimmers, and this is from Gravett and Wolnow, problem number 22 in that independent T chapter. So here are my swimmers. I had a mean of 9, and its standard deviation was 2.51. And the degrees of freedom were 8. And here's the other group, and we have a mean of 6, and a standard deviation of 2.45, and an N of 5. And I go here, first of all. For this particular data analysis, the value of Cones D then is going to be the 1.21, and that's also what I found when I did it by hand. And you're explaining 27% of the variability. Notice you could get the same thing if you knew the T, and when I did this T, I had a T of 2.11. And my degrees of freedom respectively were 9 and 6. And now I would do compute. And it's close there. There's that 1.19, that's that 1.21. And there's this 0.26. So there's going to be some rounding, and there's going to be some slight differences there. I wouldn't lose any sleep over that. What's neat here is you can find out what this means. You can go to the results whacker. and you would enter in your value of the D. I'm going to use the 1.21 as an example, and I whack it, and that's telling me that's pretty large. I love the graphic. Or if you knew the value of r, notice that's r, not r squared. You could put r in there, and it would also give that to you. So we have that. The other thing I would strongly suggest any reader or user do, he does explain the formula, and he does have references here, and there's an opportunity to leave him references. And here is a little bit about Paul Ellis. And this is where you could get his essential guide to effect sizes, and also the essential guide to power and things of that sort. He's a very helpful individual. All right, let's see if I can